So I asked you, notice in graph number 2 and 3, we saw what we call dotted lines, okay? Now, there are actually 3 types of dotted lines, and this is what I'm going to give you as the proper terms, okay? Those dotted lines that were vertical were called vertical, and the word is asymptote, so asymptote. So they are vertical asymptotes. Those are the vertical dotted lines. So that was found in graph number 2, right? These vertical ones. And then that horizontal one is called a horizontal asymptote. Okay. And what do you think about that one that was kind of sideways, going slanted? Yes, that's right. The slanted.
Really?
Yeah, it's called the slanted asymptote. Okay. Okay, so please be aware though, and this statement underneath is bold for a reason. It says for functions of this form where you have a rational expression, a numerator divided by denominator, provided that the numerator and denominator have no factor between them. Okay, so AKA also known as not graph number 4. Remember how graph number 4, the one that came out to a line, actually had a factor between them? If there is no factor between them, then you will have these asymptotes. Now, of course, you're not going to be always using your graphing calculator to find them, so how can we actually find them algebraically? Well, let me show you how today. The vertical ones you know how to do already. Do you remember how to find the vertical asymptotes? Where do we find the vertical asymptotes? So look back at graph number 2 on page 2 if you think about this. Your vertical asymptotes are at 2 and -2. Where do you find those values from? Hello? What's that? Your NPVs. That's right. So to find the vertical asymptotes, all you need to do is find, or you found them by setting the denominator, okay, equal to 0 and then solving for x, okay? AKA your NPVs, right? Also known as your NPVs, okay? So your NPVs, your non-permissible values, become these vertical asymptotes. And the equation of a vertical asymptote always is, because it's a vertical line, it's going to be of this form. It's always x equals to some number, and I'll call that number k. This is just some number, okay? Some constant, k. All right. So finding the vertical asymptotes, easy, okay? Finding the slanted asymptotes, not so easy. Now remember, a slanted asymptote occurs when the degree of the numerator, so n of x is the numerator, okay? So the degree of the numerator is bigger than the degree of the denominator, okay? And that was the example in graph number 3, okay? If you look back on page 2, graph number 3 had x squared on the top and x minus 5 on the bottom. And to figure out the equation of the slanted asymptote, we're going to use something we learned back in chapter 4, not chapter 4 of the textbook, but chapter 4 of the extra stuff that I showed you. Remember long division? Yes. So what I'm going to ask you to do is to find the equation of the slanted asymptote. Let's do long division. So x minus 5 like this, outside of the bracket, you've got x squared. Okay? So we're going to show you some long division here, and then hopefully from the end, you'll be able to discover the equation of the slanted asymptote. Okay. Anybody remember how to do this? Remember x times what gives you x squared? Anybody have an idea? X, good. And then of course we just took that x, multiplied by the x minus 5, and we put it underneath. So here we have x squared minus 5x. And then with long division, after we found that, we always subtract. So we'll subtract x squared minus x squared is 0. 0 take away negative 5 is positive 5x. And then my question to you now is, well, how do you solve for this part? Well, ask yourself, x times what gives you 5x? How about the number positive 5? And then we'll take 5 and multiply that by x minus 5. So that's 5x minus 5. We'll subtract once again, and let's see what our remainder is going to be. Our remainder in this case is going to be the number 5. Okay? Yes? Go. Thank you. Someone needs to talk to me, you know. This should be actually 25, yeah. 5 times 5 is 25. So we'll subtract to get positive 25. Thanks, Anna. Okay. Now, also remember when we did chapter 4, I asked you to rewrite this and in what they call that division statement form. So I don't know if you remember, but this can be written as x plus 5, which is your quotient, your answer, and your remainder can be written as a fraction like this, 25 over x minus 5. Okay? Don't know if you remember doing that. Well, the question here then says the following. I want you to find me what they call the slanted asymptote. Okay? Let's just look back at your graph. The slanted asymptote seems to be a line. Agreed? Can you help me with this line? Can you describe this line for me that I'm going to put in purple here? Oops, that's not purple. This is purple. What's the equation of that line? Just looking at it right now on the graph. Can someone tell me, first of all, the y-intercept for this line? And then perhaps tell me what the slope of that line will be? So you don't need to write this down in your notes. Just follow along with me right now. Let's make this bigger if we can. What's the y-intercept for this line, the dotted line? 5. Good. What's the slope? Be careful about this one, because the scale is different. I'm proposing that we can go from here to here. I see that they're going 1, 2, 3, 4, 5 spaces, but actually what is that equal to in terms of the actual length? See, this is 12. I guess this is 2, 4, 6, 8, 10. So that seems to be 10. Okay. What about going upwards here? Upwards 2 spaces, but each of those spaces going upward is equal to 5 units. So 5 times 2 is 10. What's the slope when it's 10 up and 10 to the right? That's right, the slope is 1. So what is the equation of this asymptote? It's y equals to 1x plus 5. That good stuff from Math 10. Well, going back to page 3 now, where is this idea of 1x plus 5? It's right here. Okay? So we don't worry about this part. Okay? Don't worry. We don't worry about the remainder, but I'm telling you the equation of the slanted asymptote, okay, is just the quotient, okay, is just the quotient of your long division, okay, of your long division process. So in this case, therefore, the slanted asymptote is just y equals to x plus 5. That's all. Okay. So you just need to imply long division. And then I asked you also underneath, it says, here's another note. Okay, so here's another like issue here. It says for functions of that same form when you have a fraction, okay, but notice where the numerator and denominator have a factor, okay, that's like graph number 4, then we don't get these dotted lines anymore. What we have is an open dot, and that's what they call a point discontinuity. So at a particular point, the graph is discontinuous because there's a break. There's a dot in between. Okay? Just some terminology that you'll see again next year in calculus. Okay? All right, and the last one I want to show you is the horizontal asymptote. this one's the most trickiest of them all. This is the one where we actually have to do some ideas of calculus. Oh, by the way, did you know Mean Girls was on TV the weekend?
It was?
Yeah. Wait a minute. Let me. Okay, horizontal asymptotes. All right. Now, ladies and gentlemen, the horizontal asymptotes were the ones, once again, these horizontal lines where the graph gets closer and closer to it. How do you actually find it? Well, look what happened here. Just look here with me on this graph. Okay? Do you see how I looked at this question? What is the end behavior of this function? Notice if I go really far to the right and really far to the left, you got the same thing of this number 1. Well, if I ask you to find the equation of this horizontal line, what do you think the equation is going to be? The value is at 1, 1, 1. So this idea of taking the limit, especially when you go really far out, is how you can find the horizontal asymptotes. So going on to page 3 now, back here, the formal way of calculating the horizontal asymptotes is to do the following. Take the limit as x approaches to infinity of that function, or take the limit as x approaches to negative infinity. So this is like the end behavior that we were looking at in the previous graphs. Okay? End behavior. Now, here's what I'd like us to do before we actually start working on some of these questions. What happens to these functions here? 1 over x, x squared, x cubed, and in general, for any number of n, when x goes to infinity? Bless you. So help me out. What's 1 divided by infinity? What's 1 divided by a really big number? Infinity? You sure? 1 divided by infinity. 1 over a really big number. 1 over big. That's right. 0. Okay, pretty much close to 0. Okay, now, continuing on, like what Richard said, what about 1 over big squared? Well, big squared is just equal to what? That's huge, right? So what's 1 over huge? Tiny. Still 0. Okay. Now, 1 over x cubed. So that's what? Big times big times big. That's gigantic. Okay, 1 over gigantic. That's still going to be equal to 0. All right. By the way, don't write that. Don't write big on your AP exam. They'll be like, what? Okay. Now, what about this one then? 1 over big to the power of n. Now, n could be any whole number now, right? 3, 4, 5, 6, 7, 8, 9, forever. I don't even know what that word is going to be to describe that. But in the end, what's the value going to be? It's still 0. Okay, yes, Alyssa, then Anna first. I never asked you for the power of 0. Because I don't want to tell you. If x was to the power of 0, let's just leave that for another day. Okay? I don't want to tell you right now. Anna, is that your question too, or a different one? Does x have to be a positive number? What am I saying when I use this word limit? I'm saying x is approaching this really big, infinite positive number. Yeah. Okay? So that's why, in this case, this big number is a big positive number. 1 divided by a big positive number is pretty much a really, really small positive number, or 0. Yeah, in this case, in general over here, I'll say this, okay? N has to be actually bigger or equal to 1, okay? So I'll leave that with you like that, okay? Now, we're going to use this idea a lot. Let's turn the page, and let's try to find out how you can solve for these horizontal asymptotes, okay? All right, let's turn the page. Okay, ladies and gentlemen, here's what I'd like you to do, okay? Let's do one together. I said find all of the asymptotes, okay? Not all the other, just find all the asymptotes. What I'd like us to do, first of all, is find the following, okay? Let's do the vertical ones first. I'll call them VAs. Then I'll see if there's a slant asymptote. I'll call it SA. And then finally, I'll show you how to find the horizontal asymptotes using the idea of the limits from below or from above. Okay? Okay, let's do this one first. The vertical asymptotes. This is easy. How do I find that one? NPV. So make x minus 3 equal to 0. Solve for that. X equals to 3. There's your vertical asymptote. Okay. And by the way, you see this little graph down here? Perhaps you want to actually draw in the vertical asymptote for me. So here's a vertical asymptote right here at x equals to 3. Okay. All right, then we've got this idea of a slanted asymptote. Now let's double check to see if there actually is a slanted asymptote first. In order for us to figure out if there's a slanted asymptote, I told you on the previous page that the degree of the numerator must be bigger than the degree of the denominator. Is that true? Is the degree of the numerator, which is equal to 2, bigger than the degree of the denominator, which is equal to 1? Yes. So then let's go ahead and do long division. Okay? And once again, go ahead and try this now. X times what gives you x squared? That would be x. Multiply that by x minus 3. That gives you x squared minus 3x. We'll then subtract. Okay, so x squared minus x squared is 0. 0 minus negative 3x is positive 3x. Now ask yourself, x times what gives you 3x? How about the number 3? So 3x minus 9. And that's 9. Okay. Remember, we don't really care about the remainder for slanted asymptotes. So therefore, your equation is just y equals to x minus 3. Okay. So your slanted asymptote, the slanted dotted line has the equation plus 3, x plus 3. X plus 3. It's the quotient, x plus 3. Okay. And if you could, underneath now, start drawing that line. So here's my y-intercept of 3. I guess the slope is 1. So unfortunately, the graph goes a little bit off the chart, but nonetheless, still okay. Okay. Okay, now, the last one is this horizontal asymptote. And let me try to show you this one here. Okay. This one's a little bit more tricky, and I'll show you how to do this. I don't know if I left you enough space here. We'll try. Okay. Remember, to find the horizontal asymptote, you're looking for the limit of this function. So I like you to do this, please. Copy this down. The limit as x approach to infinity of that actual function, x squared, all over x minus 3. Okay. Now, how are we going to actually calculate what this is going to be? Okay. Here's what I'd like you guys to do. For the numerator, we have just an x squared. Let's not worry about that. But the denominator, we've got this x minus 3. And my goal is to have you rewrite things with this 1 over x part. Okay? So in general, the trick to find these limits is to do this. Okay, I'd like you to, and I'll write this on the side. The trick here is to do the following. I want you to factor out the highest power of x. Okay, and do this for both the numerator and the denominator. Okay, and I'll show you what I mean by that in a sec. I'll give you a chance to copy that down. Okay. Okay, so with this, I'm going to ask you to take a look at what's the highest power in the numerator. It's x squared, right? But because there's only one term, I'm not really factoring out anything, so let's just leave it as that. What's the highest power of x minus 3? Yeah, it's the power of 1. So can you do the following, please? Richard, seriously, man, don't whistle. Okay. Okay. Factor out the x, and let's see what's left over. What's x divided by x? That's 1. What's negative 3 divided by x? Well, here's what you get. You get minus 3 over x. Okay, I'll let you think about that for a second. Okay. Is everybody okay so far? All right. Then I'm going to ask you, can you simplify this for me? Do you see anything that cancels out from the top and the bottom? The x, good. So this now just becomes the limit of x approach to infinity of x over 1 minus 3 over x. Okay. Now, remember the idea of this limit really is tell me what happens when you plug in x, getting close to this number, which I call infinity. Well, if I plug in infinity to the numerator, what is that equal to? Well, that's just kind of like infinity. What happens when I plug this into the denominator? This is still a 1. 1 minus 3 divided by infinity, or big. So what's 3 or anything divided by a really big number? 0. This number here is getting closer and closer to 0. So therefore, what I have here is I got infinity over 1 minus 0, which equals to infinity over 1. Well, what does that mean when I say the limit as x approaches to infinity means that the graph is infinity? That means as I go further and further to the right, this goes further and further up towards infinity. Is there a horizontal asymptote then? Do you see a horizontal asymptote? So actually, all these calculations show the following. Therefore, this one actually has no horizontal asymptote. Okay? So when you have the answer of infinity, that means there is no asymptote or horizontal asymptote. Okay? Why is that? Because remember, a horizontal asymptote is supposed to be a nice horizontal line, which is given by a number. What kind of number is infinity? That's way up here. I don't know what that is. Okay. Now, ladies and gentlemen, you still haven't actually sketched out this graph yet. What does the graph actually look like? Well, all you know right now is the graph gets closer and closer to these lines somehow. Okay, but you actually don't know where the graph is. So my question is, does the graph look like this? Or does it look like this? Maybe. Can it look like this? Absolutely not, okay? Because you can't cross these asymptotes, okay? The lines get closer and closer, but they won't cross. So my question to you now is, how can I figure out what the graph looks like? Well, here, you're going to have to kind of use a table of values to help you out. So for example, this is what I'd like you to do now, okay? So maybe for this graph, I'm going to put a little table of values right here. Let's just pick some values for x, and let's just pick some values for, pick some values for x to find some values for y. Here's my suggestion to you. Let's see what happens when it gets close to this asymptote. So let's take a look at this point here, 2. How about at x equals to 2? And then it might be nice to see what happens after it, so about 4. Okay? And then you might be thinking, well, what happens, maybe over here? Let's say something that's negative. Let's try negative 1 or so. Okay? And I'd like you to maybe take these 3 values and actually go ahead and plug it in to your expression to find out the corresponding y value. Okay? So we'll do negative 1 first, because that's what I want to do first. Negative 1 squared is 1. Negative 1 minus 3 is negative 4. So look what I have here as my answer. At x equals to negative 1, the y value is negative 1/4. Okay? All I did was I plugged it into the expression up here. Okay? Let's do the same thing for the other x values. When x equals to 2, we've got 2 squared is 4. 2 minus 3 is negative 1, so that's actually negative 4. Oh. So if you were to actually plot these values right now, negative 1, you're at negative 1/4, and then at 2, you're down here at 4. Knowing these 2 points, can you kind of do a quick sketch of what the graph might look like? Remember, it has to get closer and closer to these asymptotes. So my prediction is it looks like this. it probably gets closer and closer like this over here. It probably comes up somehow, and then it turns around and goes back down, getting closer and closer to that vertical asymptote. Okay? So the graph looks something like this. Okay? Now, what happens at 4 to the right of the vertical asymptote? I'll plug it in here. 4 squared is 16. 4 minus 3 is 1. That's a big positive number of 16. That's way up here. So my prediction is that the graph looks something like this. Okay, graph is up here somewhere. And this makes sense because the graph is supposed to approach positive infinity as x goes really, really big. Okay. Now, for those of you who have your graphing calculator, what I'd like you to do now is use your graphing calculator and sketch this out just to double check that this makes sense. Okay, I'm going to ask you to graph out x squared, divide that by x minus 3, and I hope that you get a nice graph that looks exactly like what you drew. Okay. Now, I don't even see this part because the graph is so high, so I'm going to change my window here. I'm going to change it to maybe like the y max of, let's say, 30, and then hopefully you can see it better. Here it goes, and then there's the other part of the graph. Okay. And if you were to make this even wider, because you want to see how this looks at the end, perhaps I'll change my window even again to like negative 100 and positive 100. And here's you go. Well, you can't see that very well, but the graph looks like this. Yeah, I won't do that. Maybe I'll go negative 25 and 25. I'll change the y value. Right? So you see the graph goes up, 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 up forever. And can you see how if I were to draw a slanted line right here, it looks like it could be a slanted asymptote. Okay? All right. Well, I'm going to ask you to try to do the next one, okay, on your own. The next one here is number 2, and sorry I didn't leave you much space. But I'm going to ask you to please find the vertical asymptotes first. And then I'm going to tell you that there actually is no slanted asymptotes because the degree in the numerator is 2, and the degree in the denominator is 2. They're equal, so there's no slant asymptotes. And then what I'd like you to do is try to find these horizontal asymptotes by finding the limit. Okay? So I'll give you a few seconds to try this on your own, please. And then afterwards, we'll get back together. Once you finish number 2, you can go ahead and try also number 3. Okay? Go. What's our vertical asymptote for this one? Well, you just make the denominator equal to 0. You solve, you actually get x equals to, and don't forget the plus minus. So there's actually 2. Okay? So for number 2, you've got an asymptote at positive 1 and negative 1. Okay? Now, next part, horizontal asymptote. This is the part where it's tricky. I want you to find the limit as x approaches to infinity of this function, x squared over x squared minus 1. Once again, I'm going to ask you to factor out the highest power of x. In this case, the numerator, there's nothing to really factor out because it's just x squared. Tony? Richard? Okay. Underneath here, we've got x squared. I'm going to factor that out. I'm left with 1 minus, and it's 1 over x squared. Okay. Notice that the x squareds here just cancel out to become 1 and 1. So now I'm asking you to calculate the limit as x approaches to infinity of the function 1 over 1 minus 1 over x squared. Well, what happens when I plug into infinity now? The top is still 1. The bottom is 1 minus 1 over infinity squared. Big squared is still big. Big, big. 1 divided by big, 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 big is 0. So that's just 1 over 1 minus 0, which is 1 over 1, which is 1. So ladies and gentlemen, in this particular incident, you have a horizontal asymptote of 1. Dot, 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 dot. Okay? So now you have to decide what the graph looks like. You can make a table of values if you wish. Or in this case, what I will do is I'll just quickly graph this out because I don't want to waste your time. But if you were to graph it out and take a look now, you get the following. Okay? So in essence, what the graph looks like is the following. You got this thing up here, and this part down here like this. Okay? All right. I'll try the next one with you. Okay, and then I think I want to just do a quick summary, and maybe I'll stop there for today. Okay? Yes. One of those curved parts. Yeah, so what you need to do is you need to look at table of values using points along the x. So don't just choose one. I would choose one value that's to the left of the asymptote. So I would have chose something like maybe -4 and maybe also -2. And then over here I would have chosen something that's between -1 and 0. So maybe like -0.5, right? So you have to pick a few points, not just one or two. Okay. All right. Last one. Let's do the vertical asymptotes, please. How do we find those? Can you factor? How about finding two numbers that multiply -2 and add to -1? Okay. So I think what we have here is x equals to +2 and -1. So I got two asymptotes once again. I will quickly sketch them out here. -1, +2. Okay. And then my question is, are there any slanted asymptotes? And I'll say the answer is no, because if you look at the degree of the numerator and the degree of the denominator, which one's bigger? It's the denominator, so no slanted asymptote in this case either. Okay. But what I'd like you to try to do now, please, is calculate the horizontal asymptote by finding the limit as x approaches to infinity of this function. Okay? And I'll give you a few seconds to try that now on your own too. I'll ask you. Okay? I'll ask you to once again factor the top. Roy, listen with me please, okay? Factor out the x squared in the bottom. You get 1 minus, and what's x over x squared? That will be the same thing as 1 over x. And then minus 2 over x squared is just -2 over x squared like that. Okay? Of course, you can simplify this, and you're left with the following. You're left with 1 over x with a 1 over 1 minus x minus 2 over x squared, like that. Okay? Now, when you plug in infinity to this thing, what happens? 1's on the top. Okay? What's on the bottom? You've got your infinity. You got 1 minus 1 over infinity minus 2 over infinity squared. What's all this infinity stuff when you have it in the denominator? That just becomes 0. Okay, now you still have an infinity in front, so it's like 1 divided by infinity times 1. That's the same thing as 1 over infinity, so what's that equal to? 0. So what you've just told me here in this case is that your horizontal asymptote is equal to 0. It's y equals to 0. It's not big, it's 0. So you have a nice dotted line right here on the x-axis. Okay? Now, I'm going to ask you to sketch this out on your graphing calculator too. Okay, and then you'll notice something even more interesting with this one. So this is x divided by bracket x squared minus x minus 2. And when you graph this one out, okay, maybe I'll actually change my window. I'll make it the same as my graph here. How about -5 to 5, -5 to 5. I'll graph this out. And notice what happens with this graph. So it seems like you've got some part down here. Okay. And then you've got another part over here that's up here. But then in the middle, it's kind of weird. Because the middle part shows the following. It shows it starting up high and then kind of going down low. And you're thinking, well, Mr. Lee, how come it actually crossed this asymptote? I thought graphs only get closer and closer to asymptotes. They don't cross. Okay. True. They don't. They're supposed to not, like, they're supposed to only get closer and closer. But what happens when you talk about the horizontal asymptote is that, hey, the horizontal asymptote just says what happens when it goes to infinity or negative infinity. That means really far out to the right and far out to the left. So technically, this horizontal asymptote doesn't exist really in the middle here. Okay. Okay. So it really only exists for this part to the right and to the left. So it's okay if it crosses in the middle. Okay. So this one's weird in that sense. Okay. Now, let me just quickly give you a summary, and then I think I'll stop for today. If I asked you to find these horizontal asymptotes, how could you do it? Here's what you need to do. Look at the degree of the numerator. If it's less than the degree of the denominator, which is case number 3, you actually have an asymptote, but it's always equal to 0. And if it's equal in degree, which is example number 2, then you actually have a value, which I'll call k. Okay? So this is a constant. Okay? And the last one is, yeah, you get infinity, but we don't say y equals to infinity. That just looks weird. So we actually say you don't actually have an asymptote. Then you have no horizontal asymptote. Okay? Because when you take the limit of that function, you'll get something equal to infinity. And we just don't know what that's going to be. Okay? So I think I'll leave you with that. And I believe on Wednesday,